Just a short introduction about our company for those who don't know us. So as you see on the slide, we have two companies altogether. It's PEG as the simulation consulting and MF Software as the software reseller and service partner. I think most of you know us, so I don't want to go too much into detail on that. Both companies are very close together, and so we can give you from consulting and software everything we think you need. Yeah, our new training, Advanced Cooling Technologies. Here you see the agenda. So we will have some theoretical points in the beginning, like about the motivation, why we should simulate, and also the simulation strategies, but also theoretical background about what happened in our injection mold with the heat flow, what are the components that are used, that are needed to control the mold temperature. After that, we will explain more detailed the different methods that can be used in Moldflow. I guess most of you know cool BEM method versus the cool FEM method, but also we want to introduce again the coolant flow function, as this is a very helpful tool for the beam cooling channels. In the simulation exercises and examples, we will show you more detailed about the workflow, how to model all the needed things, the components, and this is, as it's called, exercise, something where you also can work on the computer. You will get models from our site and can do it step by step by your own. And at the end of the training, we'll make a comparison between simulation and practice. So what are the possibilities today, but also what are the limits we see. Let's go a little bit deeper into the point. So the motivation, why we simulate and why should we simulate the mold itself, not only the part or the runner system. It's because of the complexity of the molds and the cooling system. And yeah, we know that, for example, if we have a bad mold design, we will lose part quality, but also we will lose cycle time and capacity. And always training is a way of continuing education. So you increase your know-how, you increase your skills and become a better simulation engineer. But of course, you will also get a better understanding of the processes, what happens in the mold itself. Just a few slides from here onto what is the temperature control influences. So the cooling behavior, especially in the packing phase and the cooling phase, affects our article, so the part quality and the process times. But also the cooling system affects our filling behavior if we have huge differences in the mold surface temperature. And of course, we all know that the shrinkage and warpage behavior is also impacted by the cooling system, especially for the unfilled materials, and of course less for the fiber-filled materials. So let's have a closer look to the simulation strategy we are preferring. So typically we start with the part design in the first simulation phase. After that was done, we switch in the second phase where we include the tool influences like the runner system, but then in phase 3, of course, the cooling system. That is our main part, and that is what we are focused in this training more detailed. Just give you some examples about what is discussed in the theoretical background during this training. So we will talk about the heat balance in the injection mold, what is coming in and what is going out and how. And as we are most interested in how we get the heat out of the mold, the question is, the heat transfer, how it is going. So we can say the heat is coming from the part, is going through the mold and into the water, sometimes oil, but mainly water. And what is determining the heat transfer rate? From the plastic to the mold, and also through the mold, and then again from the mold to the coolant system. And those things will be discussed in detail, how we can effect and how we can understand the heat transfer, what is determining, for example, like the material properties of the melt, how they affect the heat transfer. But also the contact quality between our part, like the plastic, and the mold wall, as this varies during the cycle and is depending on the pressure situation. And of course, we know there are differences between filling phase, packing phase, and then the cooling phase. Although the heat transfer through the mold itself, it's determined by the material properties of our mold components. And especially if you have like different inserts, mold inserts, different mold plates. So the contact between all those different components is very important for the heat transfer itself. But also, and one of the main points is the heat transfer from the mold wall to the coolant. And here we are talking about Reynolds numbers. I think every one of you heard about that. What does it mean and how it is affected, or how can we affect the Reynolds number and therefore the flow rate of the heat? And we will talk about like the capacity, which is theoretically possible, how fast we can transfer the heat through the mold and to the water. But also we will see that in reality it is limited. We have an upper limit, and that means that we have like different regions, different areas, and how they are affected in detail, and what does it mean for our process setup. Or even the temperature gradient, which depends on mainly on the flow rate of our water, will be discussed, and at the end, I guess you have a very good knowledge, a good overview, what happens in the different areas of the mold and what is affecting the heat transfer. If you know that, of course, it's easy and it's clear what we can do when we see problems, when we have deficit in a temperature situation. Also, we will discuss in detail during the training the different simulation methods we have in Moldflow. So, which way will be the best between the cool BEM and cool FEM method, and when we will use which simulation method? And of course, we will discuss the requirements for the modeling for the two different versions we have. So that means in the end, we have a different workflow, how to prepare our model before we can start the simulation itself. And of course, we will have an overview about the coolant flow simulation, as we think it's a very helpful tool, very fast, very simple. And also there are some limitations, as it can only be used at, with beam elements at the moment. And then we will go like really detailed in the different methods. What does it mean? Cool BEM, cool FEM, about the requirements, as we see here. The one on the left side, the BEM method, does not really have a mold design around, while the cool FEM always requires a 3D mold mesh. And also this can be used for a much wider range of simulations itself. For example, like multi-cycle simulations, various thermal processes, and also we can have a real 3D flow in the cooling lines. In the simulation exercises and examples, then we will have we will have models prepared for you that you will do the workflow for the different methods. You will learn again how to model all the required components. What are the differences, for example, between mold and mold inserts, and all the stuff we need in the different simulations. We will discuss also about some special conditions. What will be the effect when we have a serial connection of the water flow versus a parallel connection? What happens when we have multi-coupling for the water lines? How to model it? But also, like for the conformal cooling, what are the things to look for when we model those things? But also during the simulation results, what will be the effect, what will happen in detail. And we will discuss in detail again, what are the relevance of parameter settings to the results, also to the calculation time. So what are the settings? What can we change? What is the default in Moldflow? Why should we change some of those defaults maybe? And what will be then the effect in the result quality? Maybe there is, sometimes there isn't. And also we will see the effect on the calculation time, and that is also a very important point, not to lose time just by a bad solver parameter setting. And as it's called advanced cooling technologies, we will first talk about special processes like rapid heat and cool processes, how to set up in the different way with electrical heater elements, or even with a chiller unit that can switch from hot water to cold water, or even from steam to cold water. Or maybe how to use thermocouples to control like a heater element of the hot runner. And at least we will see what are the results available depending on the different simulation model we used, like the differences between cool BEM, cool FEM, and even within the cool FEM, we have differences between the average and the transient simulation. So we will then discuss the quality of the different simulations and what can be shown for, just for example, you see here a result which looks like the same just by the name of the result. We see on the left it's called temperature part, while on the right side it's called temperature part average. So the right side is from a cool FEM, and as it's shown in the name, average across the cycle, while the left result is from a cool BEM. And as we see, it looks like the same at the end. But also some other results look different, or maybe have different names. As for the cool BEM method, we do not have a temperature mold where we see the mold itself. The result is available, but it is shown on the surface of the part. And the mold block is not really modeled, so it's not possible to see what happens inside the mold, inside our mold components. And therefore, for example, we have to use another result in the cool BEM method compared to the cool FEM method. Just some simple result comparison. And also during this training, we will have, of course, more complex things to discuss. And that is what I just want to show you with the last picture here. Fully 3D meshed mold with all components like the hot runners, like the different mold plates, mold inserts, also the elements to keep the hot runner away from the mold itself. And for example, we see the temperature distribution and the temperature loss from the hot runner into the mold. That is much more complex situation than before. Just to give you an overview about the training, what you can expect, what will be the agenda of this new training we offer. And if you have any questions, so feel free. One point is, and that is, so I come to my last slide. The training is probably as a classroom training with 1 day duration. And on request, we can offer it also as an individual training, then typically with 1.5 days. And in the individual training, we also take your examples, your parts and molds, and show you directly on your application how to prepare everything, how to run the simulation, and to talk about the results, especially on your project. That will be the difference between the classroom training and the individual trainings. Feel free to contact us or just give your question in the chat now.